Okay, hello, this is Leg and Todd. I'm here with Brian Davis today. This is Wednesday, the 29th of April. This is lecture 21, and we're going to talk about HVAC systems. I had initially thought that we might do sort of a survey of, like, you know, some of the many different types of HVAC systems that are out there in the world. And so I thought maybe it would just be sort of a slideshow and discussion, but the truth is there's so many different system types, and to do any of them justice takes, would require a little bit of discussion about what they're intended to do and how they achieve the intent. And I just thought, we would only be able to scratch the surface anyway. So I changed my tune a little bit with this lecture and decided that we would just take a focus on a few different system types that are common for residential buildings, and kind of ignore the commercial world, where there are probably many times more different systems that we see commonly. And so we'll talk about, we'll do a quick review of why we need these HVAC systems, what they're intended to achieve in terms of space conditioning and indoor environmental quality, indoor air quality. And then we'll look at some different system types based on their intended function. And then we'll spend most of our time hopefully talking about some efficiency strategies when it comes to system selections and system design. And then we'll look at a comparison of several different system types that you might see in a residential building in terms of their energy usage and efficiencies and that kind of thing. So, what is the goal here with regard to space conditioning and indoor environmental quality? First of all, we have to ventilate. So we've covered this in some of the other lectures. We need to ventilate for air quality, for occupant comfort and health. We need to make sure that the air in the building is free of pollutants, contaminants, and that we're getting enough air exchange that we have fresh air, so the air doesn't smell bad, doesn't feel stuffy. And the code requires ventilation. We talked about ASHRAE 62.1 and 62.2. These are the ASHRAE ventilation standards that a lot of codes are based on, and 62.1 being for the residential sector, and 62.2 for the commercial. Or sorry, I have that the other way. It's the other way around. 62.1 for commercial. And of course, the International Energy Conservation Code, IECC 2012, that's been adopted by Montana, has some stipulations with regard to ventilation requirements. But despite that we have to ventilate, there is some cost associated with that, and the bulk of that cost is really in heating or cooling the ventilation air. A lot of people would jump immediately to, well, of course you've got a fan that you have to run to move that air, but the fan energy is generally speaking, is a small percentage of the total energy that's associated with ventilation. So depending on the climate, especially in a climate like ours where we have, it's a heating dominated climate, we have relatively low ambient temperatures during the winter. The temperature differential between the temperature at which we like to maintain our indoor environment, say 70 to 74 degrees, and what temperatures might be seen in the outside air, the ambient condition, that's a very large temperature differential that we have to overcome with HVAC, with heating. So it's a lot of energy, potentially. Depending, of course, you'll remember that the energy is related to the airflow rate and the temperature differential rate. So the equation for air, the nominal equation, Q equals 1.08 times CFM times delta T. So it's directly proportional, both CFM and the temperature differential. So of course, the more air you move, the more energy to heat or cool, and the bigger the temperature differential, the more energy to heat or cool. So you'll recall from previous lectures, there's a heating or cooling load that's based on those current outside air conditions, the indoor air temperature set point, however much interior heat generation there is from appliances and human beings and pets and whatever it is inside the building that's generating heat, and whatever solar gains we're getting through windows, etc. There's this total heat load for the building, and then on top of that sort of transmission load through the building envelope, we have this ventilation load. It's been a little while since we covered loads, but hopefully that's doesn't sound unfamiliar.
I'm sure you're going to probably get into it, but what is current code for the number of exchanges?
Well, so when we did blower door testing, we talked about the requirement there by the code, which is, that's a standardized way of measuring the relative leakage of the envelope, because we're measuring a leakage rate there at a pressure differential that is not normal, right? We're depressurizing or pressurizing the building to 50 pascals and then taking an air change rate at that condition, but that isn't the normal condition. So how many air changes are you going to get under normal conditions of a maybe nearly neutral or very slight pressure differential? It's hard to say. I actually don't know exactly what that correlation is. So if the state of Montana allows 4 air changes per hour at 50 pascals, what does that equate to at near zero? Like say several pascals? I don't know. I think there are ways to make that correlation, but I don't know what it is. All we're trying to do with that standard is make a standardized reference point for comparison from one building to another, so that you can say if that building sees 8 air changes per hour at 50 pascals differential and this one sees 4, then this one is certainly a less leaky envelope and is going to perform better under normal natural conditions. Bottom line is you want to minimize that. But maybe I misunderstood your question. You might be saying how many air changes are required for the active ventilation? Is that what your question was?
To maintain quality.
Okay, yeah, I'm sorry. I did misunderstand your question. That is a more complicated, if you follow the guidelines of ASHRAE 62.1 and 62.2, you determine that ventilation rate based on the number of occupants as well as the square footage of the building. So you might have, and the CFM per occupant varies from, I want to say 5 at the low end up to maybe 20 at the high end. So in a gymnasium where people are very active, or some kind of fitness center, they're going to require more CFM per occupant than they do in a library where people are more sedentary. In a classroom full of active little kids, it's higher than in a library. In a classroom of high school students, because they're bigger human beings and breathe bigger volumes of air, then you're going to require more air changes per occupant, or more CFM per occupant than you do in a grade school classroom. Okay, so but a good, like if you're just looking for a rule of thumb, 10 CFM per occupant for a typical building is not a bad place to start. And then the square footage number is a very low number of CFM per square feet. I want to say 0.6 per square foot. This is just so that even if there are no occupants, you're still replacing the air at some low minimum level to clear out any pollutants that come from off-gassing from the materials in the building. Okay. So, and we'll talk a little bit more about that actually when we get through some of these slides.
Sure.
So I'm sorry I misunderstood your question initially there, but so what we're going to see in the next slide or two, this comes right out of this document that we presented early on in the course that was put together by the State Department of Environmental Quality. This is just a brochure basically to help people get up to speed on the new energy code that was adopted, the IEC 2012 adopted in Montana. Okay, so in there they present this table among a few in the discussion about the new requirement for continuous ventilation, or well, we allow a non-continuous ventilation. We'll discuss how we do that. So this table is for continuous whole house mechanical ventilation airflow rate requirements in CFM. And so it's based on the square footage of the dwelling and how many bedrooms. Okay, so you find your square footage on that column on the left, you follow that over until it intersects with the number of bedrooms you have in the columns that follow, So if you have a house that's between 1501 and 3,000 square feet and you have 4 to 5 bedrooms, you need 75 CFM continuous. Okay. Or, this is where it doesn't, where we talk about how it does not, it's not required to be continuous. They say that if you choose not to have a continuous ventilation, meaning the fan runs constantly 24/7 at 75 CFM, if you decide to run that fan at 50% runtime, run it half the time, then you need to increase your CFM by a factor of 2. So you cut the runtime in half, you double the CFM.
Makes sense.
If you cut the runtime down to a third, then you triple the CFM. Okay, so it's just a linear adjustment. So, so they say there, for example, 1,600 square foot, 3-bedroom house requires 60 cubic feet CFM per minute, or CFM cubic feet per minute continuous, or if you run that fan half the time, it should be sized at 120 CFM. They also specify that those ventilation fans have to meet a certain minimum efficiency requirement, which is in what we call fan efficacy in CFM per watt. And so they're requiring a minimum, depending on the fan size. If it's a small fan, a 10 to 90 CFM fan, you have to meet 1.4 CFM per watt. And for larger fans that are 90 CFM and over, you need to achieve at least 2.8 CFM per watt. Okay. So there are a few different ways you can achieve the ventilation requirement in a house. You can do it with exhaust only. So this diagram kind of shows how if you were to have only an exhaust fan in the building, sized appropriately per the, like the tables that we just covered, it would tend to create a negative static pressure inside the building, which is going to result in drawing outside area in through wherever it can come into the building. Okay. So this could be through all the leakage points in the envelope, could be through an open window or an open door, and to the degree that you have a tighter envelope, well, I guess what I want to say here is that if a fan is nominally sized for 120 CFM, okay, that doesn't mean that no matter what, when you turn that fan on, it's going to move 120 CFM. Okay, that's a nominal sizing. The amount of flow rate that fan can move depends on the pressure differential across the fan, and we discussed this when we talked about fan curves, etc. So if you put a 120 CFM fan in, but you have a super tight building envelope, and it's the winter time and you've got all your doors and windows shut, that fan may not be able to draw 120 CFM of outside air. The fan might only be moving 100 or less CFM. So this isn't necessarily the most reliable way to ensure that you get the ventilation rate that you're trying to achieve.
Well, it's uncontrolled, and I imagine it could invite moisture into some of those.
And that's the other
leak areas.
Exactly. Not so moisture wouldn't be my primary concern, but you're right that you're not being able to control where this outside air is coming into the building. Mm-hmm. And what would be a greater concern to me is that if you have an envelope leakage point that happens to be near, typically we try to keep like plumbing to interior wet walls and not in the exterior walls, but some buildings do have plumbing in exterior walls or very near exterior walls. It might be that you have an envelope leak, like you saw in my house when we did the blower door test. The cabinet under this kitchen sink had a pretty major infiltration point there. So if I'm relying on an exhaust fan only to bring my outside air in, and a lot of that outside air comes in right under the kitchen sink, I could freeze the trap in that drain pipe, or even freeze a supply line, and then end up with a real mess to clean up, right, a problem to fix. So this is the simplest way to meet the code requirement, but not necessarily the best way to achieve good building ventilation.
Well, that's almost fairly standard, isn't it?
This is the standard way.
Historic, if you will.
Historically, if you go back before the most recent codes, the conventional way was to not provide necessarily any ventilation. You would have a bathroom fan, which was only intended to clear out the moisture in the bathroom after somebody showers or something. But there would be no kind of central continuous ventilation that would ventilate the entire house. So this is really a new thing, and so, and yeah, now to have a fan, an exhaust fan that maybe exhausts from, you know, you could have multiple bath fans, but you know, it's now we're starting to see more and more where it's a central exhaust fan that's exhausting at several points in the building. Okay, but if we just add into the configuration a supply fan now, so that we're somewhat controlling the introduction of outside air, and we can balance these two fans so that they're both moving roughly the same CFM, or ideally the outside air fan actually moves even just a little bit more air than the exhaust fan, so that if anything we slightly positively pressurize the house, so that we avoid the infiltration into the building at uncontrolled points. And now we've eliminated that infiltration issue. We might have a little bit of exfiltration, but that's safer as far as you know, avoiding freezing pipe problems and things like that. So we don't want excess exfiltration, but and generally, you know, in this cold climate, depending on how much of this outside air you're bringing in and where you're delivering it, you may need to heat. You might need to bring it into an air handler that can also heat that outside air, rather than just dump it in when it's negative 20 degrees outside, dumping negative 20 degree air into the house. You wouldn't really want to do that, right? So, but at least now we've got a better pressure balance, and we are controlling the entering point of that outside air into the building. Okay? And then once we've taken control of where we bring in that outside air, we can make decisions about how we're going to condition it, right? Okay. So the next step then in the progression toward improving this scenario would be, among other possibilities, but one of the better ones would be to add an ERV or HRV, an energy or heat recovery ventilator. So now we're bringing the outside air in, we're passing it through a heat exchanger where it picks up heat from the exhaust air that's also passing through and going out. Okay, so here's exhaust air going out, fresh air coming in. They're exchanging heat at the HRV. Here's your exhaust air stream going in, here's your supply air stream coming out. Okay, so we take our fresh air, bring it in through the heat exchanger, we deliver it to a supply duct, and then we deliver it to various points in the house. We simultaneously are picking up exhaust air at several points in the house and bringing it to the HRV. So HRVs that work well when they have a high, what we call effective rate, HRV effectiveness rate, they can easily make it such that in a climate like ours, where your lowest ambient temperatures get down to, you know, negative, you know, in terms of design temperatures, negative 20, negative, and even negative 30, like if you're over at Bozeman. At those coldest temperatures, if this heat exchanger is doing its job, you might bring in negative 20 air, and what comes out of the HRV is, you know, warmer than, say, 30 degrees. And so you have a lot less heating to do then to that 30-degree air to make it comfortable to supply into the space. And through much of the year, it'll keep that discharge air from the HRV closer to, you know, between 50 and 70 degrees. Okay. And it works as well on the hottest days of the year when this air, when this would be like, say, 105 degree air, and you'd really rather not dump 105 degree air into the house. At least you can knock some of that heat off of that incoming air by exchanging with the 70-degree exhaust air, bring that discharge down to maybe something more like 80 instead of 105. Okay. But in this climate, you probably still need to do some further conditioning of this discharge air. Like I said, if it's negative 20 and you're bringing this in at 30, you want to heat it up a little bit further before you discharge it. The rule of thumb for HVAC is that, or the standard is that you try not to discharge anything cooler than 55. 55-degree air is generally the lowest air discharge temp for air for like an air conditioning system when there is a cooling call. So when you want to cool the space, discharge at 55 at the lowest. Now there are air conditioners that don't have very good control on that discharge air temp, and you'll see the temp drop into the 40s, but that can cause comfort issues. Okay, with me so far? Mm-hmm. Okay, so here's a model that I put together that's just calculating the cost of ventilation for a Missoula home where the continuous ventilation rate is 60 CFM. Okay, and we have I've included in the model a DX air conditioner, direct expansion air conditioner with an EER, energy efficiency ratio of 10, and a furnace with an efficiency of 74%. So these are like, this would be like an existing building, slightly older equipment. The newest air conditioners that you're going to buy out there today should have off the shelf an EER that's minimum closer to 12. They're required by the federal government to have a seasonal EER, a SEER value of at least 13. So remember that with EAR and SEER, higher numbers better. SEER converts generally to a slightly lower EAR value. Okay, so a SEER of 13 might be an EAR of 12. Okay, and also another thing to consider is that even though they might say off the shelf this has a SEER of 13, it doesn't take very long, maybe a year or two, before that efficiency tends to drop with just the toll of time and wear and tear on the equipment. So anyway, what I've done here is I've got it's a bin model. We've covered these in the past. I've got my Missoula weather data over here. I've got my outside air conditions calculated here, which are based on this weather data. I've got the dry bulb temperature, wet bulb temperature, the relative humidity in percent, the absolute humidity in pounds of moisture per pound of dry air, and the enthalpy, which is that internal energy of the air. So I've got my internal energy of my outside air. I've got some inside air conditions. I'm saying we're going to maintain, in this case, we're assuming that we're maintaining the inside at 70 degrees all year. Okay, and I'm doing similar calcs on this inside air to get, I'm assuming a relative humidity and then calculating an enthalpy and internal energy of the return air. And then I've got a ventilation rate, 60 CFM across all bins. And so now I can calculate the load, the ventilation, basically the load, meaning the amount of heat that's required to heat this outside air to this inside air condition. Any outside air that comes into the building, whether we actively heat it with an air handler, say at a furnace or coil, hot water coil or something like that, whether we heat it at the air handler or not is irrelevant, because once it comes into the space and we have to maintain the space at 70, ultimately we have to heat that outside air up to 70. Okay. We can heat it up to 110, and drop it into the inside condition where it offsets some of the heat losses through the envelope, or we can dump it in at some cooler temp, and ultimately we have to heat up the inside air anyway. Okay. So this load is just the total load, so the sensible load is that 1.08 times CFM times delta T. So just taking the difference in these dry bulb temperatures at each bin times the CFM of 60 times 1.08 gives us this sensible load. And then our total load is a different multiplier, I can't remember what it is exactly right now, but 4 and change times CFM times the difference in enthalpy gives you your total load. Okay. The total load is important only if the air conditioner has to do some dehumidification. Okay. Anyway, so then what I do, I think you can see the whole thing here. I take I apply the maximum, the total load to the DX air conditioner where we have to cool that outside air. So up here in these top bins, the outside air is coming in at 95, 85, and we're trying to cool it down to 70, so that's a load on our DX system, our air conditioner. But as soon as that outside air gets to be below 70, okay, then we have to heat it up to 70. And when it's really below 70, like down here it's at, what does that say, negative 25 or 35. So, in Missoula we only have 1 hour of the year, typically, when the air temp is that low. But now we've got 60 CFM and a much bigger delta T, and so that's the biggest heating load we're going to see. So you sum all these up and you multiply by utility rates. I use 0.07 7 cents per kilowatt hour for electricity and 90 cents per therm for natural gas. You apply your efficiencies, so in the DX case it's the EAR, and in the furnace case it's that AFUE. And let me just say as a caveat here, generally it's really not the best thing to use these standard published nominal efficiency rates for energy modeling like this. But in a rough model, just trying to make a point where I don't have better information about how much energy what the efficiencies of those systems really are, it's the best I've got, so I'm using it, okay? So it's the model, it's not a perfect model, but it's a decent model. And so what you'll see here is that the air conditioning is relatively cheap for that 60 CFM. And keep in mind, this is not the total air conditioning cost for maintaining the building at 70 degrees. This is just the ventilation load. Okay. There's another load that has to do with how much heat we're gaining or losing through the building envelope and the windows and everything that it isn't shown here. So this is only showing how much the air conditioner would have to run just to cool down this 60 CFM of ventilation air, and how much the furnace has to run just to heat up the 60 CFM of ventilation air. Okay, so we end up with 25 kilowatt hours or $2 a year for the air conditioning, and 226 therms or $205 a year for the heating. Okay, so if you think about, for a lot of us, we might spend on our heating, somewhere close to, depending on your house size and efficiencies and everything, but let's say $100 a month during the winter months. Okay, so let's say in a year you spend $600 on your furnace bill. This says that the ventilation might be a third of that. So maybe a third of your heating bill is just for the air that comes in through the as ventilation, driven by an exhaust fan or by whatever system you have to bring that in. But and then there's an infiltration load that I'm not showing here as well. But okay, if we go then to hot, humid climate, I didn't specify a place here. I just kind of made one up. Okay. Here we see that a lot more of the hours are clustered up here in the warmer temps. We don't have any hours down here in these really low temps. The lowest it ever gets is 0 in this climate model. More hours there than I probably should, but whatever. It's like I said, I just kind of constructed this one. And same calcs, right? Same EER for the air conditioner, same efficiency for the furnace. Now it just shifts, right? Now we're doing a lot more air conditioning because we're a hot, humid climate, and a certain amount of dehumidification. So now we're spending, $176 a year on air conditioning. We're only spending $31 a year on heating, but again, the total is $207 a year. Okay. So if you're in a hot, humid climate, you're going to pay for ventilation, but you're going to pay in air conditioning. If you're in a heating-dominated climate like Missoula, you're going to pay, but you're going to pay mostly in heating. Okay. And obviously, to the extent that you can improve these efficiencies of these systems that have to do that heating or cooling, you save.
Mm-hmm.
Right?
Absolutely.
Okay. So here's, and now the point I want to make here is that, in this course, again, we focus on residential buildings. So somebody might say, well, $200 a year, it's not that big a deal. It's not a ton of money. Somebody else might say, well, actually, I could really use another $200 a year in my pocket.
I was going to say $200. That seems like it's a pretty efficient building, isn't it?
Again, just the ventilation. Well, that's not your building energy. Just not your total building energy. Just ventilation. 60 CFM. Just what the bathroom fan is pulling in.
Yeah, that's quite a bit.
Okay. And again, this brings home that notion. When you talk about cost of ventilating, like I said, a lot of people jump right to the fan.
Yeah.
Well, that 60 CFM fan at 2.8 watts per CFM, a couple bucks a year, a few bucks a year. All the cost is here in the heating and cooling.
In conditioning the indoor air.
So, but now let's look at a commercial building. Okay, and this could be a school, or I've called it a 400 occupant office building. Okay, there are office buildings around here with 400 occupants in them. In fact, I think there are some of these more, but DirecTV is a good example. Yeah. Okay. So you were headed in the same direction. But certainly there are school buildings with 400 occupants, right?
Should.
Okay. So if we assume 10 CFM per occupant is the ventilation rate, then that means we've got a 4,000 CFM of ventilation rate. So same kind of calcs. I've still got DXAC at ER at 10, and I've got a boiler at 74%. And now we're looking at, what does that say, almost $2,900 a year. So, the 200 in your house, it might sound affordable. This becomes a real burden for big buildings with a lot of occupants who don't necessarily have, everybody's budgets are different, but a lot of our school buildings are pretty strapped for money, right? So here to an even greater extent, improving the efficiencies, or even looking for ways to, do we really need 10 CFM per occupant, or when do we need 10 CFM per occupant? Are we ventilating when we don't actually have all those 400 people in the building, right? So you look for ways to improve this situation. Okay. Okay, so again, that discussion there, and maybe this is a good time to check my TechSmith relay and start part 2. Yeah, felt perfect.